Hello, Professor. My name is Luis Gustavo Marin Gomez, and this is my video format for the MAE 103 final exam. It is approximately 12 o'clock at midnight, so I'm not at the best of my. I'm not full. So problem number one: system is shown to bring water from a reservoir to airstream. Air is incompressible. That's one of the assumptions I made. Find an equation for the velocity of air in the pipe, V air, for which water reaches to pipe and begins to mix with air. So I used the Bernoulli equation. The 2 points, one is where the pipe, uh, where the reservoir pipe goes up. That's the first point. That's point number one. Second point is outside of the other pipe, of the larger pipe. And so using Bernoulli's equation, I saw that V2 was the velocity of the air, and V1 is unknown. P1 was unknown. The Z's were the same. I chose same height, so they would eventually cancel out. But the P2 was the gauge pressure of the atmosphere, which was 0. So so that would eventually cancel out. Then I got something, V air squared is equal to 2P1 over rho air plus V1 squared. And I had that as equation number one. And then from the notes, week 3, lecture 2, you had something like a conservation of mass type of thing that said Q1 is equal to Q2. Therefore, V1A1 is equal to V2A2. So I used that equation, and I came with the conclusion that let me see, D1 squared. Well, it's a circular pipe, so uh, it's pi over 4 times d1 squared times v1, but the pi over 4s they cancel out. So then d1 squared times v1 is equal to d2 squared times v2. If you use the labeling thing that I used, what's it called? Oh my gosh, I'm sorry, I'm not at the best. The labeling, the 2 points, there we go. We found, and by simplifying for V1, we found that V1 is equal to D2 of the pipe times the velocity of the air all over D2 of the throat. Then you apply that equation to the past equation and simplify, and you get something. I got something in the format of um, V air is equal to 2 times P1 all over rho of air times 1 minus d to the fourth power of the pipe all over d to the fourth power of the throat. Oh my gosh. Then I used manometry from week 2, lecture 1. P1 is equal to PATM plus rho GZ. In this case H. And I found that P1 was equal to rho of water times G times H, the V air. Then I applied that to the P1 so that they were all in terms of the question. Now problem 2, I'm not gonna lie, I had difficulty drawing the control volume and I couldn't even start it, so I just moved on. Now let's see. Problem 3, water flows at 300 liters per second at 10 degrees Celsius. Is to be conveyed through a commercial steel pipe with a total head drop of 6 meters. Minor losses are given to be 12 v squared over 2g, g being 9.81, where v is average velocity. What is the diameter of the pipe? For this, I used a combination. The assumptions I made: laminar flow. Sorry. I also used Reynolds number. Reynolds RE is equal to rho times velocity times d all over mu. Mu being dynamic viscosity. I found that through through a couple of searches. Rho being 0.9975 g per centimeter cubed, and the viscosity through 1.3808. So then I also used what's it called? Oh my gosh, I'm forgetting this stupid formula. I forgot the name of the formula. HL is equal to HL major plus HL minor. Through all of that, I had the HL minor, the head loss. There we go, head loss. Head loss minor was 12 times the head loss minor was given. Head loss major was unknown, but there's a formula for it. The formula for it is that the friction factor times length v squared all over 2 times g all over 2 gd. Using that formula, and then the head loss is equal to the 6 meters, the original 6 meters that is given in the problem. Wrote that down. Then with Reynolds number, since we assumed a laminar flow, we found that the friction factor was equal to 64 over Reynolds number, and then we plugged that into the equation, the head loss equation that I was using. And we did some work to simplify and make it more, we could pull some stuff out. I got stuck somewhere around here because I almost forgot about one of the D's, but like a couple of, like an hour or two but later, I saw my mistake. Then I used the flow equation. Q is equal to the velocity times A times the area. Area of a circle is pi over 4d squared. So then, and the Q is 300 liters per second as given from the problem. I changed that to meters cubed per second, which is 0.3. After changing that, we got that 0.3 meters cubed per second is equal to the velocity times power 4d squared. Simplifying the velocity times d squared is equal to 0.3 meters cubed per second times 4 over pi. You can use that given value to plug into the formula that I just talked about, and then you can simplify and find the velocity, which in my case was 3.09 meters per second. After you have your velocity, you just plug it back into the flow derived equation, and to get a diameter. And in my case, after all the calculations, I got a diameter of 0.35 meters. For problem 4, large reservoir. I didn't really pay that much attention near the end, so near the end of the lecture, so I have no idea how to do number 4. So yeah, I would just like to thank you, Professor. Well, you're probably not gonna watch this, so, but I'd like to thank whoever's grading me or whatever, and the professor. Thank you. Have a great night and happy holidays.